Swayam Prabha. Digital India. Educated India.
Hello everyone. Now our present topic is blending delay time. Here we will discuss blending delay time in the blowroom stage. So before we proceed, let us first try to understand what is blending delay time. Okay. So blending delay time is actually between two locations in the yarn manufacturing process. It is a maximum possible difference in time at the feed point between two tufts of fiber that can come adjacent to each other at the delivery point. Now, there is a feed point. So, these are the feed points. Okay, different fibers has got their different feed points, but at the delivery point there is a chance. So, this fiber is close to this delivery point. So, this fiber will come closer quicker, this fiber will be transported longer length. So, this fiber will get chance reach here at different time than this fiber. So, the blending delay time does not take care of this issues, where the fibers are having the chance of getting come adjacent to each other, that is the important. So, maximum possible difference in time at the feeding point, okay, between two tufts. So, two tufts have their at the feeding point it will be at the different point different time, that difference is there. Like suppose this is a fiber, there are different chambers. This is 1, 2, 3, 4, 5, 6 chambers are there, 6. So, here is a fiber, okay. These are the fibers, okay. Now, this fiber will reach here. So, these are the different chambers are there, okay. Now, try to see here, this is the fiber here feeding, this fiber is fed here, and this fiber will reach, this is the delivery point, okay. So, each other at the delivery, this is the delivery point, okay, delivery point. So, it has to reach, if this fiber is reaching to reach here, it has to cross this point, this point, this point, this point. So, 1, 2, 3, 4 point, then it will come. So, it is moving in this fashion gradually, fibers are moving in this fashion, then moving in this fashion. So, this is the passage of fibers, okay. So, this fiber will take certain time to come, but here is another fiber, it is also trying to reach here. So, if you see, this fiber is coming vertically to reach the delivery point, but whereas this fiber bunch is coming to reach there. So, if there is a possibility, if the timing same, this fiber coming from the 6 number of chamber to coming to this delivery point, and another fiber in the at the bottom portion, the chamber 1, this fiber will travel horizontally. So, this is travelling almost vertically towards the delivery point. So, their chances of coming adjacent to each other is more. So, but this fiber is fed earlier. So, maximum possible difference in time of feeding fed earlier than this fiber. This fiber is fed later, because feeding in the chamber through the feeding system is in this portion downward. So, the difference in feeding time, that we will calculate. So, that is the, because here this is important, because it will give intimate blending. So, this fiber is blending with this fiber, this is coming together. So, this is the higher the blending delay time, means better is the blending, chances of blending of different components. So, this is the mixing battery. Okay. Here you can see the fiber, as I have mentioned, material flow. Material is actually fed in this fashion, then the conveyor is coming. So, this is suppose 1, 2, 3, 4, 4 chambers are there. So, material is fed vertically, but it is transported from the bottom. So, material is coming at the top of the chamber, but delivered from the bottom in the horizontal. So, what is the material flow? It is fed from the top, moves vertically downward, then it is transported horizontally. This is the process of material flow in the mixing chamber or blending chamber. So, if the bale openers are provided with weighing equipment, then different types of fibers can be blended. So, here not only cotton, different types of cotton, but polyester cotton. So, polyester cotton can be blended. So, different types of fibers can be blended here. So, here it is a photograph, you can see. Now, these are the different fibers, different components shown by different colors. So, 1, 2, 3, 4, 5, 6 chambers are there, and at the end here it is a delivery point. The feeding point is here, okay. Feeding point is here. Now, you can see the fibers at the leftmost point, okay. The fibers is forming the lowermost layer, lowest layer, then followed by just above that this fiber from this is chamber 1, 2, 3, 4, 5, 6. So, from chamber 1 fiber follows forms the lowermost layer, then above that the fiber layer from the chamber 2, then chamber 3, then chamber 4, and chamber 6. From the segment chamber 6 it forms the uppermost layer, and after that this layer, then there is a blender is there. So, which actually blends the all these fibers together. So, we can have, and here the fibers are coming from the opener. So, you can see the different layers of fibers here, and then the after blending the fibers are blended at random fashion, almost in homogeneous fashion. And this is a multi mixture, the same process is there. You can see here there are 6 chambers are there, 1, 2, 3, 4, 5, 6, 6 chambers are there, where fibers are fed from the, this is the fiber feeding line, okay, and as we have discussed that there is a different processes there. First we fill one chamber, then similarly the other chambers are filled. So, that is a feed tunnel is there, one is feed tunnel, then closing flap is there. So, when the fibers are filled, so we are the flap is there, it is a closing flap, then then fiber will come to the next one like that. Okay. Closing flap is there just to control the fiber filling. Then mixing chamber is there, this is the 3 is the mixing chamber, here here is the mixing chamber. Then feed duct is there, 4 is the feed duct, through the duct the fibers are fed. Feed duct, then light barrier, so which is actually controlling the fiber feed. It will, if it crosses, then fiber that the closing flap will be activated, the feeding will stop at that chamber. The exhaust air funnel, okay. So it exhaust air will be there because it is a excess air, because after feeding the exhaust air will be there, otherwise there will be pressure developed. Perforated plate is there, then and then it is delivery roller is 8 is delivery roller at that point. So, these are the perforated plate and delivery roller, and then opening roller, this is the delivery roller, here is the opening roller, okay. 9 is opening roller and blending conveyor. So, this is the fibers are coming vertically and then conveyor, through the conveyor it is travelling towards the delivery point, okay. And blending duct is there, this is 11 blending duct. Then metering conveyor and material suction funnel, this is suction funnel is there, and then this is a cleanomat excel. So, here actually we are getting the blended product, blended material, okay. Chambers are filled successively, okay. One by one it is chambers are filled. Once it is the chamber 1 is filled, then chamber 2, in this way it will be filled. Materials removed from the all chambers simultaneously. So, successively it is filled, but simultaneously the materials are removed from the chambers. Opening rollers open the flocks. So, here opening rollers are there, they are opened, then it is blended. Now, we can see here the unimix is. So, in the this chambers are there, you can see in this chamber the different layers of different fibers are stacked. Okay. Now, then the diversion of the tufts of mass are at 90 degree. So, it is going vertically downward, then 90 degree horizontally, it is a diversion is there, causes the shift of these layers in terms of space and time. So, this is actually shifting is taking place. We can, it is very, and this results a long term blending, okay. Upright lattice simultaneously extract the tufts in all layer. So, this is upright lattice which actually extracts the fibers from all layer, okay, different layers. This gentle opening process is actually its results in a second random blending of the tuft. So, it is a random blending, yes, it is there, and this blend is already homogeneous at this stage. So, here at this stage only in the unimix, the blend we get it is almost homogeneous. After even after that we have carding, we have other process. So, we get very intimate blending at this unimix system. The free tapped undergoes the third intensive blending on the opening roller zone. So, opening roller zone there is another blending is there. This additional thorough blending process ensures consistent and homogeneous fiber blend. And also this curved path at the bottom of the chamber helps further improving the blending delay time. So, it actually increases the blending delay time because of the longer path. So, earlier we thought we discussed that it is directly it is at a 90 degree it travels, but due to this curve it travels a longer path. So, it increases the blending delay time. So, that means this fiber will reach at this stage at this stage delivery stage at the longer time after because of the longer path. Now, we will see how to calculate the blending delay time, which is very important. Now, our assumptions are we will consider only 6 chamber multi mixture, 6 chamber is there, then continuous feeding type system. The feeding type system will be continuous system, this is our assumption. Normally it may or may not be continuous feeding system, but for our assumption it is a it is a continuous feeding type system. And time required to fill. So, 6 chamber is there and time required to fill is say assumed to be 3 minute. So, per unit volume. So, per unit there in the chamber in one chamber it can consist of different unit volume. So, for unit volume it requires a 3 minute time. Now, we will consider different cycles. For first cycle, this is the condition first cycle of feeding this that first it is getting the 3 minutes time. Okay. So, this is the 3 minute time per to fill the 1 unit. Okay. So, here you can see this is requiring 3 minutes time. Next we are considering its this will be removed from this side. So, that is why here the right side chamber should be filled properly, 100% filling will be there, but it starts from the back side. So, 3 minute time it is required. Then this chamber, the chamber 1, 2, 3, 4, 5, 6. So, chamber 2 will have 2 such unit. So, 3 plus 3 6 plus 3 9 minute time is required. Then chamber 3 will be there, 9 plus 3 12 15 18, then 21 24 27 30 30 33 36 in this way 30 45 46 48 51 50 and ultimately 63. So, this is the time required. So, that means here it is a 3 minute is required, but at this stage after 63 minute this chamber will be filled. So, this chamber is filled in third 3 minute. This chamber to fill this chamber it requires 63 minutes. Now, here blending delay time is 45. How come it is 45? Because you can see this is, if we remove this, you can see this one and this one, it will actually, it is the feeding time is, this is 41, 48, and if we subtract from 48 and 3, it will be 45 minutes blending delay time. And similarly for second cycle, you can see here second cycle. So, 63 is there, and then 66, 69, 72, 75, 80, 75, 78 and 81. And here the blending delay time will be 57 minutes because of the fact. So, what you are doing? So, 60 maximum blending, what is blending delay time? Blending delay time is the maximum time required difference. So, here the difference is this is maximum 48 and 3, the difference is 45, that is the maximum possible delay. So, here in this row 66 and 9 is there. So, the difference is 57 minutes. So, 66 minus 9, the difference is 57 minutes. Now, let us see the third cycle. Third cycle will be, we can see 60 and this is the third cycle. So, earlier it ended at 81, now it is becoming 84, 87, 90, 93, 96, 99, 99. Now, in the for the third cycle, the blending delay time will be 66 minutes. Why 66 minutes? Because it is 84 is the maximum. Which one will be minimum? Minimum is 18. So, 18. So, difference will be 66. Okay. Now, for next one, next cycle, it is actually now this is taking out, we are taking it out. Okay. Now, it is coming, the next will be layer will come lower bottom. So, 72, 87, okay, 70 to 87. Now, here you can see here, and this is 30 becomes here, 45 will be here, 42 will come at the bottom, 60 will come here and 57 will come. So, one layer is coming out. Now, here now 99, then 102, 99 plus 3 plus 315 plus 308 plus 311 plus 314 and 117. So, after 117 minute, this chamber will be filled, although we are removing the fibers from the bottom continuously. Now, if you see here, in this case fourth cycle, the blending delay time will be, the maximum is 102 and minimum is 30 in this way. So, difference is the 72, that is the blending delay time. And now, you can see the for fifth cycle and sixth cycle, this is the condition. Okay. So, same thing, it has come down and it has become the diagram become. So, here you can see, let me go back. So, fifth cycle it is, and sixth fourth cycle. So, third cycle, fourth cycle. Now, this will be removed, this will be removed. What will happen here? It will be 70 will come, 75 will come at the bottom for the fifth cycle, 75 has come. Now, you can see here, now the when once it will go, this chamber will be totally empty, then this chamber will be filled, and this chamber will be filled by the new layer. So, here which is shown by the pink line. So, 117, then it is filled here 120, 123, 126, 129, 132. So, from 120 minute to 130 minute, this total chamber will be filled. Okay. Now, here if we see the blending delay time, here we can see, we have to see the maximum time required 120, 120 is the maximum and 45 is the minimum. So, blending delay time will be 75 minutes. Now, once we remove these things, this chamber will be empty, then it will be filled by this chamber. Now, here we can see this will come removed, 78 will come bottom, 93 will come at the bottom, 108 will come here, 123 come here, and this chamber is filled by the new feeding, and then 63 is coming here. Now, here if we see the maximum and minimum, what is maximum here? Maximum is 138 and minimum is 63. Now, here interestingly we see the for sixth cycle is equal to the fifth cycle. Earlier what we have seen, the blending delay time is consistently increasing in every cycle. We can go back to first cycle 45 minutes, second cycle 57 minutes blending delay time, and third cycle it is 66 minutes, fourth cycle it is a 72 minutes, okay. And but in fifth cycle it is becoming 75, and sixth cycle also it is 75. That means it has got saturation. So, the basic thing is that the blending delay time increases till n minus 1th cycle, where n is the number of chambers. So, here number of chamber is 6, n is 6. So, blending delay time will increase till n minus 1, that is fifth cycle. After that blending delay time become flattened, it will not, it will be constant. Okay. So, this is the physically it has been described, but now let us discuss in generalized form. General form is that this is known as stabilized blending delay time, SBDT. So, blending delay time when it is getting stabilized, that is called stabilized blending delay time for sixth cycle, for sixth chamber, and the time of fill is sub 3 minute. The stabilized blending delay time is 75 minute. Okay. So, you can see for 6th compartment, for 8th compartment, for 10th compartment. So, for 6th compartment the blending delay time reaches at 5th cycle. For 8th compartment blending delay time reaches at 7th cycle, and for 10th it is reaching at 9th cycle. So, n minus 1 cycle, for n is the number of compartment. Okay. More compartments, better is the blending, that is higher blending delay time will be there, but more compartment requires higher space. So, that is optimization has to be there. Now let us discuss the generalized form of blending delay time. So, this time the earlier what we have discussed till now, it is with an example, but if the blending delay time changes, like filling time changes or number of of this chamber changes. So, what will be the generalized form? Now, this is the generalized form. So, x is the time to fill, x is the time to fill, and n is the number of chambers. Now, x is the time to fill. So, x, 2x, 3x, 4x, 5x, 6x. So, 9x, sorry 6x, 7, 8x, 9x, 10x, in this fashion it will go, okay, for filling. Now, here we can see, so for n minus 1th column it will take x. So, there are different column, it will take x plus 2x plus 3x up to n minus 1 x minutes to be filled. Okay. So, this is actually n minus 1th column. So, if we add all these things, so you will get n into n minus 1 by 2, it is a arithmetic progression. So, just simply add 1, 2, 3, 4. So, we will get n into n minus 1 by 2 multiplied by x, if we take x common, and up to n minus 1. So, this is n minus 1 up to the, and next will be the this plus x. So, n into n minus 1 by 2 into x plus x, this is the nth column. So, this is n minus 1th column, then n next column is this one. Now, what will be the blending delay time for n, for this nth column? So, this section. So, blending delay time is the, this is the maximum time and this is the minimum time. As we have seen, this minus x will be the blending delay time. So, we can see blending delay time is this one minus x. So, ultimately blending delay time is this one, okay, n minus n, n multiplied by n minus 1 by 2 multiplied by x. This is the blending delay time for this generalized form, okay, for first cycle. This is for first cycle with the n number of n minus 1 column, and x is the time required to fill. Now, for second cycle the similar thing will happen. So, here you can see this as n into n minus 1. Now, it will be, so n into n plus 1 by x, ultimately it will come there, but here you can see n into, so next will be n into n plus 1 by 2 multiplied in x multiplied by x plus x, the next column will be here. So, it will keep on going and it will be n x, n is the number of column. So, it will go on increasing x, 2x, 3x, 4x. So, here n number of stacks are there. So, blending delay time will be, again this is the minimum is 3x and maximum here is this one in that column, lower column. So, it will be this minus x. So, blending delay time will be n multiplied by n plus 1 by 2 x plus x minus 3x. So, that is the, so ultimately now we can see for n equal to 6, n is the column chamber, n is the 6 and x is the x 3. So, for second cycle blending delay time will be 57, that we have already checked. Even earlier case if we see, let us go for the first cycle, here blending delay time is n is 6, x is 3. If we see n is 6, 6 multiplied by 5 divided by 2 multiplied by x 3. So, it becomes 45 minute, that we have seen for the first cycle it is 45 minute. For the second cycle we have checked the generalized formula is this one, this is the generalized formula, but for our earlier example if we try to check it is becoming 57. Okay. Similarly, for third cycle same thing will continue, okay, and this one is the minimum, this is the maximum one can see, and the ultimate 1x, and this will become after nth layer, this is there, and the blending delay time will be this minus this maximum minus minimum, this is the blending delay time. And here for n equal to 6 and x equal to 3, we have checked that for third cycle it is becoming 66, we have already seen physically. Okay. And for fourth cycle again the same process will continue. So, here the maximum is this one at the bottom and minimum is here 10x. So, it will be for sixth cycle it is 72 for fourth cycle. Now, for fifth cycle again it will be there, fifth cycle again this one will continue. So, this minus this is maximum, and here is the maximum is n into n plus 1 by 2 x multiplied by 3 n x plus x minus 15x. This is the blending delay time for fifth cycle. Okay. And for n equal to 6 and x equal to 3, this is 75. We have already seen it is 75 is the blending delay time for fifth cycle with n number of chamber 6 and time to fill for unit is 3 minutes. So, same using the generalized formula we are getting this one. So, now generalized form of blending delay time for expressed for third cycle, this is the third cycle. Okay. For fourth cycle that we have already explained here, third cycle is this one, fourth cycle is this, and fifth cycle is this, which is actually saturated blending delay time. So, for fifth cycle this is here. Now, this is saturated. For generalized form again if we want to get this for n equal to 6 chamber, this is the generalized form. So, this 3 can be arrived at n minus 3, n is 6. Okay. So, that is how we get, and 15, this 15 can be arrived as n minus n multiplied by n minus 1 by 2, that means it is 6 multiplied by 5 by 2, it is a 15. So, 15 can be written in this fashion, n minus n multiplied by n minus 1 by 2, and 3 can be written as n minus 3. This is the generalized form for the blending delay time with any number of cycle. For 6 chamber the standardized blending, this is the standardized SBDT, standardized blending delay time, this is the generalized formula. Okay. For 6 chamber standardized blending time occurs at fifth cycle, and we get the term 3x for filling time of 3 vertical columns. So, 3 nx, okay, this 3 nx we are getting. So, it can be generalized n minus 3. So, that is 3 equal to. So, that is why we are generalizing n minus 3. Similarly, for this n multiplied by n minus 2, it is actually 15 can be 15 term 15 can be generalized, that is n minus n multiplied by n minus 1 by 2. So, that we are getting in this fashion. So, total overall generalized formula for blending delay time is this one final. So, this is the blending delay time with n and x in terms of n and x is that n multiplied by n plus 1 by 2 multiplied by x plus n minus 3 into n minus x plus x minus n multiplied by n minus 1 by 2 multiplied by x. This is the generalized standard blending delay time, which is actually used to calculate the blending delay time standardized. So, just for by rearranging this we get this is the generalized formula, and in this form we get. So, and this gets cancelled out. Okay. So, many things will get cancelled out, ultimately we are getting in this form, and this is the final generalized formula x multiplied by n minus 1 square, and this is the standardized blending delay time. So, we can get the maximum blending delay time by using this formula. So, for say 8 number of chambers and say for 5 minutes, 5-minute delay time, 8 for 8 chambers, n equal to 5, x equal to 5. So, we can get 5 8 minus 1 square, 5 into 49. So, that will be the standardized maximum blending delay time for this type of situation. Okay. So, what we have derived? We have derived the standardized blending delay time and blending delay time. So, this is standardized blending delay time is maximum blending delay time can be achieved. So, that way we should not go beyond that. Okay. That is the maximum blending delay time achievable. So, this is the standardized blending delay time. So, n chamber for n chamber 6 and x 3 the time required to fill one volume. So, this is the standardized blending delay time 75, okay, and we are getting this as a 75 is the standardized blending delay time. So, so here if we see x is 3 and n is 6, that means 3 multiplied by 5 squared, so 75. So, 75 we are getting here by using this generalized formula. Okay. And I think that is all about the blending delay time, and so you can get it. So, we will stop here, and in next class we will start another topic which that is we will continue with this blending which is uniformity of blending or mixing. Okay. Till then, thank you.